We've got Weston Pace. He is an open source software engineer at LanceDB. He is on the PMC for Apache Arrow and Substrate and has spent an unhealthy amount of time thinking about how best to read data from cloud storage. Recently, he has been helping develop the Lance file and table formats and studying how random access, multimodal data, and search can be integrated into the modern data lake. If you've got questions, we'll hold the Q&A at the end, so just hold tight for that. Again, I'd like to introduce Weston Pace. Thank you so much.
Thank you. All right, let's get started. So I'm going to be talking about data loading. I wear a couple different hats. For most of this talk, I'll just be wearing my pretentious data engineer hat. So I'm not going to be going too hard onto any one particular solution. And I'll try and highlight when I'm talking about something that's LanceDB specific versus just the general problem of data loading. And I am semi-local, so I drove up this morning. I have the lumberjack regulation plaid that you get issued in Olympia when you move there. So we'll just get this out of the way first. LanceDB is a database, like many, many, many databases. It's built on the Lance file and table format. We do a lot of work on kind of large data types, so images and video and how you can work with those effectively. And we look at like ML workloads, which data loading, which I'm going to be talking about today, is an ML workload. Again, I'm not going to go into too many of the details of LanceDB in particular in this talk, but we have lots of stuff online if you want to learn more about it. So what is data loading? I think every AI open source and probably closed source project out there seems to want to be involved with data loading in some way. And people complain about data loading, and we would hear about it a lot. And it's kind of confusing to understand what all of the roles that all the different pieces play here sometimes. So I grabbed this Scooby-Doo meme because there's like a library out there, Hugging Face Accelerate. And if you pull the sheet off, it's just like a thin wrapper around PyTorch as data loader and how they do multiprocessing data loader. They just kind of configure it correctly and wrap it in another data set. But then if you were to look at that PyTorch multiprocessing, it's going to be using a data set. And so sometimes you can rip the sheet off again, and underneath that data set is Hugging Face. So there's a lot of projects that are involved in a lot of different ways. It can make the landscape somewhat confusing. And at the time, it was something we had to figure out. It still is. And I was rather confused because this is data loading. You open a table. You create a model. Sometimes people talk about fine-tuning, so that's just you load an existing model. And then you go through your table. Every batch in the table, you call a train function. And it's never called train. It's called forward or something confusing. But it processes the batch of data, and then you go grab the next batch, and you process that. That is data loading. Hope you enjoyed the presentation. Unfortunately, that did not work. So I work a lot on open source projects. And if you work on open source projects, all of your trauma comes from random things that random people say to you. And we would get a lot of comments like, this LanceDB project is great, but I wish it had something for data loading. And I was just kind of like, what do you want? Or someone would write something and be like, oh, this is good at this and this and this, but it has no integration for data loading. And it's kind of like, again, it's like data loading is just going through it. So there's something else that's going on here. There's some other kind of complexity. And we would run into customers, and we would say, potential customers, what do you want help with? Like, you're a new kind of startup. You say, what can we do that will convince you to give us money? And they say, well, solve this data loading problem for me. And again, it's like, what's the problem? So that's what the talk is about today, is mainly like why it's not quite so simple as this, and what challenges are introduced, and how we're starting to solve those challenges. So let's go ahead and take a look at some of the struggles that we run into. Data scientists often are working with pandas, with data frames. They do a lot of their scientific work, initial work, with stuff that just completely fits in memory. You've got maybe a million images, which I guess a million images doesn't completely fit in memory, but it's close. All their data is on their laptop, or it's on some kind of NFS drive at the university or something like that. And so you get all these examples that are like, OK, so we're going to run through, we're going to do this loop. I guess I missed the for epoch and epochs. They go through all the data like 100 times, because it just helps get them more data. And they say every time we go through the loop, we're going to completely randomize the order in which we read the data. And now you go to all of these companies that have large amounts of data. They've got billions of rows. They're in Iceberg. They're in just some kind of columnar storage, usually, these massive data sets online. And you say, I want to go through all of my data in a completely random order. And you start to run into trouble. Another problem you run into is you've got to be able to split your data set into different pieces, training and validation. Often you're only training on a subset of a larger data set. So this will be, people want to create a, maybe it's like an image generation model. And they want to create a new image generation model to make cat memes or something like that. And so they have, within their company, billions and billions and billions of images in their giant data set. And they say, well, first thing I'm going to do is just grab all the ones that are cats. Yeah, training on many different servers. We want it to be distributed. And we often have to transform our data. And so these things can introduce challenges that we run into data loading that we can look at how we solve, which we broadly are going to group into two categories: permutations and pipelines. So for this discussion, at least, these are the things that I'm going to be talking about, which is, all right. Yeah, and then before we get there, I think everyone went to the keynote where they explained how to give a good presentation, and so everyone has that in their brain. And now I have to give you a presentation. So he delivered a bad joke. I'm going to deliver 3 jokes that are worse. So it's kind of close to Halloween, and I feel this is also a little bit like a Thanksgiving jokes here, because the Thanksgiving tradition is you have family members that don't agree and they fight. In the data world, we have data frame people and we have database people, and they always seem to be fighting. So how do you scare someone that loves data frames? This is not even really a joke. This is the worst one. You should just tell them it doesn't fit in memory. And now their data frame library no longer works. There's like 50 different libraries that will make data frames work with stuff that doesn't fit in memory, but they all do it in different ways, and it gets complicated. How do you scare someone that loves databases? There's a lot of SQL DB admin types out there. You want to scare them? It's very simple. You just ask them for the 31st row. And you're going to get a well, actually talk very quickly about how there is no such thing as order in a database, and the 31st row is a meaningless distinction. A data frame person would be like, what's the problem? How do you scare someone that loves columnar formats? You just ask for the data in random order. And there's sort of a bonus joke here. It's kind of like an undercurrent for this whole talk is how do you scare everyone, is you just tell them that databases and data frames are the same thing. And that's just guaranteed to irritate anyone. So if you need to start a fight at your Thanksgiving data family, then yeah, just go for that discussion. All right. And these are really the problems that we're going to be talking about. It doesn't fit in memory. There's this weird concept of order, and we need it to be randomized. So what we're doing is we're going to tackle this with permutations, which, again, this is a fairly straightforward math concept. I have my table here, and I'm pretending it's a data frame. So I do have, we can talk about row 3 and row 2 and so on. And, there's really nothing fancy here, is I can pick several different ways that I could iterate through these rows. And I could also choose that I don't want to go through all of the rows, just 0, 3, and 2, 1. And so permutation is very simple. It's just a list of numbers. And that's all I have to kind of figure out. that expresses a lot of what I need to do. It's, if I need to split the data set, well, one split will have this set of numbers and the other split has this other set of numbers. If I need to shuffle, I just shuffle those numbers. And if I need to filter, I just take some of the numbers out. And that's really all we're talking about here when we're trying to set up this data loading is we just different ways of arranging which rows do I want to read and in what order do I want to read those rows. So I spoiled it, but as you can see, there's just, there's a lot of things that are not permutations that are still going to happen, and I'll be talking about those in the next section when I talk about pipelines. So things like column selection and post-processing, that's more in like the transformation step. So first we can look at how do we express these permutations. Most data loading examples and tools and libraries and tutorials are not going to say, step one, create a permutation. They create it very implicitly, and so it gets kind of hidden in the details. So the example on the left there is what you'll see a lot of times. You probably won't see exactly that nowadays because PyTorch data loader is going to hide all of that within, but it's doing this internally. So for ID and shuffle range of num rows, blah, 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 blah. That shuffle range of num rows, if you look under the hood, it actually has to generate the entire range of rows that you have and then shuffle it in place just because of the way those algorithms work. So you actually do have a permutation in there somewhere. A lot of times with an implicit permutation, you're filtering rows kind of after you load the row. And so there's some pros and cons when we talk about explicit permutations where we can kind of avoid that. And I'll get a little bit into that later. An explicit permutation is just, OK, I'm going to figure out my permutation first, and I'm going to write it down. And that's what we're doing at LanceDB, basically, is first thing you do if you want to do data loading is you create a permutation. And that's just a table. And you've got a column of row IDs and a column of split IDs. And that's it. And the row ID is not exactly the data set offset, but the details don't matter. It's close enough. It's a primary key, basically. And so you can do this with just about any data set. There's nothing special to LanceDB. You have a column of primary keys and split IDs, and then you have to find some way that you can read those in a sequential order now, but we'll come back to that. And then you can distribute this. So now you have many different workers. Well, they all share one permutation, and they all just read a slice of that permutation. And you don't even have to have them read random parts of the permutation because you only need to randomize once. So like worker 1 can read the first 10% of your permutation, worker 2 reads the next 10% of your permutation, and so on and so on. Now you might wonder how this works when we have implicit permutations where we're not actually defining something that we can pass around to the different workers. So what you will see out there, if you read a guide on like distributed PyTorch, what happens in most of those guides is every single worker will get sent the seeds that are used for the randomness, and they will all go through and they'll generate the entire array of indices, and then they will shuffle it in the exact same way because they're using the same seed, and then they will slice off. So they just all regenerate their view of that permutation. With an explicit permutation, it's usually a bit more straightforward. It's just a table. All of your workers have pointers to that same permutation table. All they need to know is like, where do I start and where do I stop? So they can take that slice and they can figure out what data that they need to read. So there's a lot of ways you can make this more complicated, and I will briefly touch on that in some of the later slides, but this is the basic idea. It does introduce a few more challenges in addition to what I was just talking about. When you're doing distributed data loading, you need some kind of coordination layer that's talking about all of your, it basically tells all your different workers to go start, tells them which ones to collect. When you're training the model, you often have to send the model state between the different workers to kind of synchronize and communicate. When you're doing distributed anything, then failure is pretty much guaranteed, especially now. Everyone wants to use preemptible instances because the other ones are just way too expensive. So you have to deal with that, and you got to regularly snapshot the overall progress, So these are just, they're kind of tangential challenges, but there are other things that you'll run into when you're trying to do distributed data loading. All right, so that is step one, which is how do we figure out which rows each of our workers is going to process and load. And step two is this data transformation stage that happens. And we can have both pre-processing and post-processing. Kind of snoozing a little on pre-processing because it's not super relevant to data loading, but the idea is that you do your processing before you store it in the database in the first place. So when you're doing data loading, it's already done for you. You just grab the stuff that you already calculated. Post-processing is after I load it out of the database, but before I put it into the model, I have some kind of work to do. And I should have talked about this at the introduction. I'm a data person. I know very little about how these models actually work. I talk to data scientists often as part of my job, and they will go on and on and on and say things like tokenization and normalization, and all I hear is blah, 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 blah. This is just computation that has to happen to take the data from one form to another form before they stick it into the model. And they usually do it inefficiently, and then they blame us. So I'll come back to that. Terminology is not standard. I've heard some people call it pre-processing, post-processing. I've heard online and offline processing. There's probably other ways to talk about it as well. Tomorrow, I believe, Jack, also from LanceDB, is going to be talking about feature engineering. So check that out. It's one way that you can take some of this post-processing work, which can sometimes become your bottleneck, and you can shove it into pre-processing, which is like, instead of calculating your features on the fly, calculate them and store them. All right, so we've now covered the what. We have to iterate through our data in a random order. We often have to transform it. And now we can start talking about performance. We can start talking about some of the challenges that we see. So there's this golden rule of performance, fool's gold, trying to be a little punny here. You probably should not follow it. It's not really meant to be a great rule. If the GPU is busy, then it's the model's problem. Or to put it another way, it's the data scientist's problem. If the GPU is not busy, then it's your problem. This is anytime the GPU is not busy, data loading will get blamed. That has been my experience. So people will say, my GPU is running at 20% efficiency. This data loading is really slow. And then everyone just immediately assumes it's an I/O problem. I will say at least, sometimes it is, at least half the time, it's this transformation stage that's the bottleneck and not the actual. So I bristle a little bit when I hear this sometimes because it's not really a data loading problem. And so this is, we had a user once who came and he said, I'm doing data loading and it's running very slowly. I'm only getting like 10 rows per second. And we went back and forth again and again and again. And eventually we found out that in this stage, he was loading images and he needed to scale the image down, normalize the image. Like the image was just bytes, so he had to decode it into a raster. And all of that work was happening and it was taking a very long time. And so I said, oh, well, there's the bottleneck. And I thought my job was done. And the user came back and said, well, how are you going to fix that? And it's like, well, we're a database. This is a Wendy's. This is not our problem. But that doesn't work. So it is something that we need to think about. And it turns out it's something that it's a general problem that databases are kind of used to solving, which is we talk about pipelines. So here's our starting stage of that user or many other users that I've talked about. Hopefully no one is doing this exact process, and you'll see what I mean on the next slide. But your basic initial data loading pipeline, I'm reading something from storage. I have to decode it, take the bytes and turn them into like a PyArrow table. I have to normalize it and tokenize it and just other things, who knows what. Then I put it into the GPU. The GPU is going to train the model. I've got all these little horizontal lines here because the GPU is massively, infinitely, probably not infinitely, but I don't know the details. A lot of parallelism. So you stick it in the queue for the GPU to process. It chunks away as a parallelism, and then you get something that's extremely slow. And so, most people have figured out, well, don't read from storage one batch at a time. You need to parallelize that step. So now we kick off a whole bunch of I/O requests. If you're reading from S3, you probably want to have 100 plus I/O requests per server that are going off to grab your data. Then that goes into a queue. And then we decode, normalize, tokenize, and you train your model. And it's better, but it's still pretty slow end to end. So the next step I will see people often run to is this just sort of general assumption that CPU slow, CPU bad, GPU fast, GPU good. And so they say, well, we're just going to throw all this work onto the GPU. And things will get a little faster. It gets a lot more complicated. But that's not really the performance optimization we need to perform here first. So the first thing that we need to do is we need to just parallelize that transformation process as well. So what we have here is 3 different pipelines. Your I/O pipeline, your CPU pipeline, or your transformation pipeline, and then your model training is kind of a GPU pipeline. The details here are going to vary a lot from model to model and thing that you're working on. The parallelism between all 3 of those is going to be wildly different. Your kind of I/O parallelism is going to be based on what you're reading from. If you're reading from cloud storage, you need tons of it. If you're reading from NVMe, you don't really need all that much of it. Your GPU parallelism is going to be usually based on how many parameters you have and how the actual model training algorithm works and things that go into, again, that area that I don't really know about. Your transformation parallelism is usually just based on how many CPU cores you have. Here we're doing batch-based processing, so we read a batch off. As soon as we have enough I/O to create a batch, we throw it in the queue, we start processing it. We want all of our cores running it all the time. Once you have 3 pipelines, then performance problems, no one is saying that you can't then put it back on the GPU after you've got that middle pipeline. If you want that middle pipeline to run on the GPU, you're certainly welcome to. I don't know if it will make things faster or not. From my personal experience, it just makes things more complicated. There are certain workloads where it can be important. And to kind of help you guide this decision, I have a little bit of performance numbers moving forward here that'll kind of show when you might want to think about doing something like that. Yeah, and let's jump straight to those. But the idea here is we've got 3 pipelines. Once you have pipelines like this, we can start talking about throughput. So essentially, your far left pipeline, we have the I/O throughput. How fast can you read the data off? And we can just express that in, let's go ahead and jump. I/O throughput, you're always going to see it in gigabytes per second, megabytes per second, bytes per second. When we talk about transformation, sadly, everyone always just refers to it in rows per second. And then we talk about the model training, and now we're talking about tokens per second. These things can all be converted back and forth if you're willing to just fudge and make some assumptions as to how big of a row is and how big of a token is. But we can start at the top with I/O. That's usually more simple. Sequential I/O, you're talking about gigabytes per second. I don't care if it's cloud storage or NVMe or whatever we're talking about. It's going to be in the range of 1 to 20 gigabytes per second, probably. If you're doing random I/O, you can still get gigabytes per second if you have an NVMe disk. If you have a spinning disk or if you're reading from cloud storage in a random order, then it really depends on your data. If you're reading just straight up numerical data, you're in the kilobytes per second range. If you're reading images or video, then it's actually not too hard to get up to gigabytes per second again. So again, there's a lot of variation here, and it might kind of affect how you're going to do things. Transformations, who knows? Very application dependent, often far too application dependent to figure anything out. And then model training. This one was surprising to me. If you convert those tokens per second numbers, which we're talking about even at kind of like the top speed models, we're training at rates of maybe hundreds of thousands of tokens per second per GPU. We're talking about megabytes per second of data. Again, here I'm making a grossly simplifying assumption that one token is equal to about 10 bytes of data. It's going to vastly depend on what a token means, and it can be application specific as well. But a lot of the model training things I've seen are running at like megabytes per second. So this is something that's often surprising to me when people talk about data loading and how hard it is to get. It should not be that hard to get megabytes per second of data into the GPU so that it can run at full speed. It is still today surprisingly difficult to get everything configured correctly. All right, we're making some assumptions here. If you're doing things like reading an entire video and then extracting a 10-second segment from that 2 GB video and then passing it to the GPU, then obviously your I/O will look very bad, but you're just not being very smart about how you read your data. There are ways that you can just read that 10 megabytes you want instead of the entire video. So you got to make sure to do all those things. So if anyone has to solve this data loading problem, step 1 is to really figure out what these 3 numbers are, figure out where your bottleneck is, and then you just keep iterating until these go down. When we talk about distributed performance, nothing changes too much. One thing that changes is you often have many GPUs per server. So you want to make sure that your any sort of CPU pipeline that you have needs to run, if you have 10 GPUs, it probably needs to run 10 times faster than your GPU throughput. So if your GPUs can handle 100 megabytes per second, then you want to make sure your CPU pipeline can handle a gigabyte per second at that transformation. The other thing you might run into if you're a giant company is all of these servers can, all these I/O numbers are for like one server to cloud storage. If you have hundreds of servers that are connecting to cloud storage, you will start to learn that there are things called service account limits, which control how much you can pull from cloud storage across all of your machines instead of one machine. And so you potentially hit I/O bottlenecks there. So that's something to be aware of if you're going to train at a massive scale. Evaluation is just more data loading. It looks almost exactly like what we had before, but instead of model, we'll call it a scorer. And we're going to go through our data. Usually you can do it sequentially. You don't have to worry about random access so much anymore. But the important thing about evaluation is it gives us these cool charts that everyone likes to look at. I did not draw the left picture. I did draw the right picture. And you'll see these a lot. The left one, you can call it like a learning curve or a loss curve. And we're kind of showing that each pass through our data, we go through our validation split and we test how well it does on some metric. And we test on our training split how well it does on some metric. And so you should see pretty quickly you'll get better and better and better. There's lots of different shapes that curve can take, and it tells you things about maybe you're overfitting or underfitting. Your ML scientists will tell you more about that. If you're coming from a data engineering point of view, the most important thing here is to kind of help you decide if you have 2 or 3 different ways of solving this data loading problem. You can compare them using these curves. And then there's also accuracy, where instead of looking at how fast something converges or what kind of patterns we get, you're just looking at a raw score at the end of the day. I did 100 steps. How good was my score? And so we can use these metrics to answer questions like, do I really have to shuffle my data? Can I just read through it sequentially? Because then I can read it much quicker. And so there's some cool research out there. I like this one because they called it Corgi Pile. And I just assumed that was named after the dog. But it's not. There's something called a Corgi Shuffle. And then the pile came from some other thing. And then they just mashed it. I think it's actually someone's name at the end of the day. I'd have to look into it more. They found something interesting, which is like, oh, if I shuffle every epoch, it really doesn't give me much better of a score, really any different score than if I just shuffle my data once. The goal is just to get rid of those patterns between things. And so this can help you kind of make your decisions on if I/O is your bottleneck, can we get rid of shuffling? Should we look into this Corgi shuffle, which is a way to do sort of block-based shuffling where you still have some sequential but some random? Well, again, start with your 3 numbers. If I/O is the bottleneck, then you set up your evaluation. Then you compare the 2 options. If you're still getting good enough scores, then you use the cheaper shuffling, and you're good to go. You can process things faster. You can also cache. And I am running low on, say, 5 minutes left? All right. There's 2 different ways that you can cache. You can have a caching service, which is you have a ring of very fast storage between your object storage and your workers down at the bottom there. This is very simple. You can support kind of any model of, you can do fully random access. It's persistent. These things can stay up for a long time. It does require infrastructure, though, which I guess that's the 5th joke. It's like, how do you make a university student scared? Or actually, how do you make any kind of data scientist scared is you tell them that they have to talk to the infrastructure team. If you have to set up a persistent server for something, that just scares people. Usually it means money. For us as LanceDB, it means money. So, if you want this cool caching service, I'll put my LanceDB hat on. This is something that we are offering and investigating, and it's definitely a way that we can speed up and make training simpler. There's another way you can cache that's 0 infrastructure, which is you just cache on the workers themselves. So there are some libraries that do this well. Mosaic Streaming and Hugging Face both do this kind of model where they'll download it the first time, and then all of the epochs after that are going to run on the local data. Hugging Face, you have to be able to fit your entire training set on each worker. Mosaic does something kind of like the Corgi Shuffle, where you have these blocks, and you only have to fit, each worker gets its own block. But so again, limited shuffle options or small data. It's a little bit more constraining, but it's 0 additional infrastructure, and that's always fun. All right, so we are starting to implement some of these things in LanceDB. Now, this is the last 2 slides where I have my LanceDB hat on. We've got permutations here, so just an easy way to kind of configure a permutation, and then an easy way to read that permutation in order so that you can do your data loading. And there are things that we're looking at in the future, which is like maybe we can offer some of these shuffle algorithms. Maybe there's some way we can help with that transformation process. It looks a lot like a query engine. It's just another pipeline. So is there some way that you can fit that into your database? And then, yeah, just better ways to join external data. So, questions?
How do you customize the? Can you customize the permutations with LanceDB?
Yeah. So when you create the permutation, you have to define. There's, I think, 3 things. There's a filter, there's splits, and there's shuffling. And for the splits and shuffling, there's a couple of different options. So when you shuffle, you can just shuffle all of your rows, like a deck of cards, complete what you would expect from shuffling. You can also do what's called like a clumped shuffle, which is where we'll take groups of 50 rows and we'll shuffle them around. That way you still get some sequential access, but you get shuffling as well, and you can kind of balance that. And then splitting, there's lots of different ways that you can calculate splits. So like if you just provide ratios, it's just going to randomly assign rows to try and get 5% in this one and 95% in the other one. Sometimes people want those splits to be more persistent, but also handle new data coming in. So you can define your splits using like a hash function on some columns. So like a hash function on your image URI, which means that now if some image was in split 1 before, you added a bunch of new data to your table or deleted some rows or something, that image will still be in split 1. So it's a little bit more stable. So there's some configuration options. And you can also just say, use this column to figure out what my splits are. So if you want to calculate them in some completely weird way, you just store that as a column in your table, and you can use that.